So now we're going to talk about the idea of electric current. And the way I want to introduce current is to go back to an example that we've been looking at with the electric potential. And the examples drawn here, I've got two equal voltage lines. I've got a plus 10 volt line and I've got a 0 volt line here. And I'm placing a positive charge essentially at the plus 10 volt potential line. And in our previous discussions, we've recognized that, all right, that positive charge will accelerate to the right. The electric field is pointing down the potential hill. And so that charge will accelerate to the right and it'll speed up and it'll be moving with some speed by the time it reaches that 0 volt line. But what I wanted to do is I wanted to write out our conservation of energy expression here. So if you remember back to 101, the change in the energy, so the final energy minus the initial energy, is equal to the work done by the non-conservative forces. And so, of course, if there's no work done by non-conservative forces, E final equals E initial, and you get conservation of energy. So if I write out the individual energy terms, final and initial, I can rearrange them to write out that the work done by non-conservative forces is just the change in the kinetic energy plus the change in the potential energy. Where again, if the work done by non-conservative forces is 0, you get this expression that we've been using, that the change in the kinetic energy has to equal the negative of the change in the potential energy. But I want to ask a different question. What if the change in the kinetic energy is 0? And you may say, well, how would this be possible? How could this charge go from the left-hand side to the right-hand side without speeding up? And the answer turns out to be more obvious than you might originally think. We saw in 101 the possibility for objects falling to the surface of the Earth to reach terminal velocity, where the objects would be falling to the ground, losing potential energy as they fall, not speeding up, and that's because all of that potential energy was being converted into thermal energy due to the drag force of the object moving through the air, rather than being converted to kinetic energy. And so in the case where the kinetic energy isn't changing, the change in the potential energy is equal to the work that's being done by the non-conservative forces. And the reason I want to bring all that up is because what we're going to do is we're going to have our charges not just in free space moving between voltage lines, but in a material, in a metal, in a wire. And in that scenario, as the charges move through the wire and lose potential energy, they will not be speeding up as they move through the wire. They will be generating heat. So they'll be moving at a constant speed. You can think of it as a terminal speed, but it's called a drift velocity. They'll be moving at a constant speed. And so that loss in potential energy is related to the thermal energy that's generated by the wire or the system. All right, so all of that being said, we need to define a quantity current because we're going to have charges that are moving now. And so we define average current here as the change in charge over time. So that's essentially keeping track of a specific spot, say in your wire, and counting the number of charges that zip by and divide by the amount of time that you are counting. And of course, if you do that over some large time interval, this is really an average of the current. So if you want the current at any instant, then you need to take the derivative, dq dt. And so our current, just looking at the quantities, our current unit is going to be a coulomb per second, which we define as an ampere. or an amp. All right, and so here's our picture for current. And so it turns out that you can describe everything that we're going to be talking about with circuit analysis. You can describe as the positive charges moving in the direction of the electric field, or the negative charges moving in the opposite direction of the electric field that's set up in the wire. And you'll get the exact same results for all of our analyses. Historically, current is defined as the direction that the electric field is pointing in the wire, which means the current is defined as the direction that the positive charges would move through the wire. All right, so we're actually adopting this picture over here on the left. So I mentioned that the charges can move through the wire without actually speeding up, even though they're moving to lower potential energy. And the reason for that is because the charges are colliding with the material and essentially generating thermal energy. And so this brings up the idea of a drift velocity. And so the collisions are, again, the reason why the charges as they move through the wire do not speed up. The potential energy that is lost as the charges move through the wire exactly corresponds to the thermal energy that's generated from these collisions. Right? And again, this is analogous to terminal velocity that we talked about in 101. And so the drift velocity for a given material depends on the current that's flowing through that material, and then divided by NQA, and the free charge density, and Q, the charge carrier, and A, the cross-sectional area of the material. And the last thing that I want to mention right here is a quantity called the current density. So the book treats the current as a scalar quantity, just the amount of charge moving through the material. But you can define a vector quantity, the current density, which corresponds to the current per unit area. And so I've got this picture over here. So I've got the current density drawn with flowing to the left, and the cross-sectional area there, A. So if you integrate J over that area, then you get the total current flowing through the material. And so, of course, if the current density is uniform, then you end up just getting that the current density is the current divided by A. All right, so if charges are moving through a material, I think the most obvious question to ask is, do charges move equally well through all types of material, or do charges move more easily through certain types of materials? And so this brings up the idea of conductivity and also resistivity. And so I've got this piece of material where there's a voltage difference between the left and the right side. So you could think of this basically as hooked up to a battery. And therefore, you've got an electric field set up in the material, right, pointing from left to right. Well, in many materials, when you set up an electric field, the current density that's produced is proportional to the electric field that's been set up. And this actually is the ultimate explanation for Ohm's law, which we'll talk about in the next video. So the current density is equal to the electric field multiplied by this constant called the electrical conductivity. And the electrical conductivity is specific to the material that you're using in the example, right? So it's material specific. And so one thing I want to point out is that sigma here has units of whatever the unit of current density is divided by whatever the unit of the electric field. And so current density is current per unit area, so amp per meter squared, and the electric field, volt per meter. And so we end up with the electrical conductivity having units of amps per volt meter. And we're going to introduce a new unit here called the ohm. And this is essentially the unit that goes with resistance. We'll see in just a minute. And so if we introduce the ohm unit, then sigma has units of 1 over ohm meter. So sigma is the electrical conductivity, and it turns out that often in electronics and in circuits, instead of talking about the conductivity, we talk about the resistivity, and that's just simply 1 over sigma. And so the units of sigma are 1 over ohm meter, and so resistivity is just ohm meter. You just flip it around. All right, so conductivity and resistivity are inverses of each other. Both of the quantities are determined by the material that you're investigating. And so the resistivity, again, since we have this definition, the resistivity is related to the electric field divided by the current density. And one thing to point out is that for many materials, the resistivity is temperature dependent. That is to say, as the temperature increases, the resistivity is essentially a measure of how difficult it is for charges to move through the material. And so the higher the resistivity, the more difficult it is to move. With the conductivity, since they're inverses of each other, the higher the conductivity, the more easy it is for charge to move through the material. And you can see that directly from this expression right here. If you set up a voltage difference across this material, then the electric field is automatically set up, and so sigma determines how much charge density you get. So a larger sigma value, a larger conductivity, you're going to get more current in that situation. Since resistivity is the inverse of conductivity, the larger sigma value gives you a smaller resistivity value, right? So a smaller resistivity means it's easier for charge to flow. So taking a look at this picture from the book, I've got my piece of material hooked up to a battery, essentially the same picture that I had above. I've got the electric field direction drawn. I've got the current density direction drawn. In this case, the current, right, is flowing from left to right through the material. And I've got those little current arrows drawn. And the left side of the material is at high potential and the right side is at low potential. And so let's just look at what happens when we follow just the algebra and the definitions that we've already given. So the electric field is related to the resistivity multiplied by the current density. And the electric field, for a uniform electric field, the electric field is just equal to the difference in voltage divided by the separation of those voltage lines. And so that's the delta V over L from the picture. I've got my rho still, and then I substitute out the current density, I over A for J. And then I just rearrange the terms, and I notice that the change in voltage across this material is equal to I multiplied by this thing in parentheses, rho L over A. And so that allows us to define a quantity called the resistance, which depends on the resistivity of the material, the length of the material, and the cross-sectional area of the material. And so this resistance, which has units of ohms, is the typical quantity that we refer to when we're talking about circuits and circuit analysis to describe how difficult or how easy it is for charge to move through an object. And I've got this written over here. Since rho depends on temperature, the resistance of your wire or your material actually will have some temperature dependence as well. And down here at the bottom, I've highlighted this relationship. So this is, in general, the definition of resistance is if you've got some element in your circuit where there's a voltage drop from the left side to the right side or across the element, then the resistance is defined as the difference in voltage between the two ends divided by whatever current is flowing through that element, whether it's a resistor or whether it's a light bulb or any variety of circuit elements that we end up looking at in this course. The resistance is defined as the voltage drop across the element divided by the current flowing through.